All right, for this first problem here, we have a situation where there's a firefighter running towards a firehouse at some speed while the fire alarm is sounding. We know from the Doppler effect that that's going to lead to a change in the frequency heard by the firefighter. So we have the velocity of the firefighter here. In this case, the firefighter is the observer. So this 15 meters per second is going to be the velocity of the observer. The source would be the firehouse itself, which obviously is not moving. And then this 740 hertz, that's going to be the frequency of the source itself. That's the actual frequency emitted by the firehouse. And we want to figure out what frequency the firefighter hears. So we're going to go ahead and set up our equation for the Doppler effect. The Doppler effect tells us the frequency observed is equal to the frequency of the source times V plus or minus VO all over V plus or minus VS. So let's go ahead and work through that. So we're looking for the frequency observed. We know the frequency of the source is 740 hertz. That's the actual frequency emitted by the firehouse. V is the speed of sound in air, so I'm going to put in 343 for both of them. And then I'm going to input these values, velocity of the source and the velocity of the observer, and then I'll think about whether or not I'm doing plus or minus. So the velocity of the observer, that's the firefighter, that's going to be 15 meters per second, as we see here. The velocity of the source is 0, so it doesn't really matter if it's plus or minus. It's going to be 0. Plus 0 minus 0 doesn't really matter. So that part we don't care about. We do, though, want to figure out, should we be adding or subtracting this number on top? So what I always keep in mind is any motion towards is going to ultimately increase the frequency. So what I want to think about is up top here, on the top of this fraction, do I want to add or subtract to increase the frequency? The answer, of course, is we want to add. That's my way of always figuring it out, but certainly you can, make some notes and you'll start to pick up on this the more problems you do like this. So frequency of the observer is going to be equal to 740 times 343 plus 15, which is 358 over 343. And that ultimately is going to give me an answer here of 772 hertz. So that will be the frequency actually heard by the firefighter, even though the frequency of the source is only 740 hertz. Let's go ahead and work through this next one here. So for this one, we have a tuba player running down the hallway at 20 meters per second. That's going to end up being the velocity of the source here, because the tuba player is the thing making the sound. And they're playing a note here that's a frequency of 440 hertz, and so that is the frequency of the source itself. And what we want to know is, what is the frequency heard by a stationary observer, meaning they're not moving, while the tuba player is running towards them. So we're going to start with our equation, and that is the frequency observed is the frequency of the source times V plus or minus VO over V plus or minus VS, where VO and VS are the frequency of the source and the observer. So we're looking for the frequency observed. We know the frequency of the source is 440. We can go ahead and fill in this V here. That's the speed of sound in air, which we're going to say is 343. That's always the number we're going to use unless otherwise noted. And then we want to fill in what these two velocities are. So the velocity of the observer is 0 because they're stationary, and the velocity of the source is 20. Now that we have that, I'm going to decide whether or not it should be plus or minus. So for the top, it doesn't really matter because adding or subtracting 0 is irrelevant. But for the bottom, we do need to think about whether or not it should be positive or negative. And the rule of thumb we always remember is whenever the motion is towards, that leads to an increase in the frequency. Okay. In this case, they are running towards, so we should end up with a greater frequency observed than the frequency of the source. So what you have to think about, and this one's a little bit trickier, but think about the fact that this plus or minus is on the bottom. In order to create a bigger number, we want to actually have a smaller denominator. We want to divide by a smaller number. Okay? And so For this first one, we're actually going to subtract on the bottom, and that should lead to a frequency observed that is greater than the source. And when we go ahead and do the math, it's going to be 440 times 343 over 323, and we end up getting a frequency observed here of 467.2 hertz. So that works. That is always a nice little check. Just thinking about it conceptually, you know it should be greater, and we ended up getting a greater number. Okay, so for the second part, I'm going to be using the same equation. It's still a Doppler effect situation. The only thing that changes is now the source, the tuba player here, is running away. So it's really just going to be one quick change. So I'm actually going to take this basic equation that I had here and go from there. We're just going to have to think about our signs once again. So I can say the frequency observed is going to be 440 times 343 on the top and the bottom. That's still the speed of sound. The observer is still stationary. The source is still moving at 20. The top still does not matter because the observer still is not moving. All we need to think about now, though, is what's going to happen on the bottom. Should we be adding or subtracting that 20? And so now we know we have a situation where the source is running away, and away leads to a decrease in the frequency. Okay, and so when we're running away here, what we want to do is we want to actually add on the bottom. And the reason we're doing that is that's going to mean that we're then dividing by a bigger number, and dividing by a bigger number means we're actually going to end up with a smaller frequency. And so when we go and actually do this math here, what we end up getting is the frequency observed is going to be 440 times 343 over 363 now. And when we solve that, we get the frequency observed when the tuba player is going away is going to be 415.7 hertz. All right, so for this first one, we have an organ pipe that's closed at one end, which means we're employing the L equals m lambda over 4 equation, where m is 1, 3, 5, etc. For the different harmonics. This results in a pattern within the pipe that looks something like this for the first few harmonics. So it's fixed at one end, free to oscillate on the other end. So there's your first harmonic, which is a quarter wavelength. Your next one is 3/4. Your next one is 1 1/4 wavelength. So it looks something like that. So that's what we're dealing with this organ. We know the pipe is 1.22 meters long, and we want to determine the first 3 harmonic frequencies. All right. So what I'm first going to do is I'm going to determine the first 3 wavelengths that we would hear. Okay, and then from there we'll be able to determine the frequencies. So the first 3 we're going to hear correspond to the first, the third, and the fifth harmonic. Remember, with open closed, you only have the odd harmonic values here. So for this first one, we can say 1.22, that is the length every single time, equals 1 times lambda over 4. And so in that case, when we solve for lambda, we'll see that lambda is going to be 4.88 meters. For the next one, we can say 1.22 equals 3 times lambda over 4. And so when we go ahead and solve for that one, we're going to find that lambda is going to be equal to 1.63 meters. And then for the last one, 1.22, and now our m is going to be 5, so 5 times lambda over 4. And when we go ahead and solve for that one, we're going to find that lambda is going to be equal to 0.98 meters. So from those lambdas, we can go ahead and solve for our wavelength, or our frequencies, using that wavelength and using the fact that the speed of sound in air is 343 meters per second. So now that we have all the wavelengths, we can calculate our frequency by just using the equation velocity equals wavelength times frequency. We know that the speed here is going to be 343, so any wave that's moving through the air is going to be moving at that speed, unless it's noted otherwise. We've talked about somehow it does change with humidity, temperature, etc. But here it does specify to use 343. So we can say that 343 is going to be equal to our wavelength, which is 4.88 times our frequency. And so we end up getting a frequency of 70.3 hertz for that first one. For the next one, when our wavelength is 1.63, we find that our frequency would end up being 210.4 hertz. And lastly, we end up using that 0.98, and when we use that 0.98 as our wavelength, we find that our frequency is going to end up being equal to 350 hertz. And so those would be the first three harmonic frequencies that are heard, including the fundamental, which of course is this first one right here. All right, so for this next problem, we're looking at a cello, which is a closed instrument, which means we're using the L equals m lambda over 2, where m is going to be 1, 2, 3, and so on. And so based off of that, we want to go ahead and try and find the velocity, knowing that the third harmonic plays this particular frequency. So let's think for a second about our third harmonic. We have a string fixed at both ends, so that third harmonic is going to look like this, a standing wave with 3 humps here, basically. And so we can say that that length of the string, 0.69 meters, is going to be equal to m, which in this case is 3 because it's the third harmonic, times our wavelength divided by 2. So we can say that 1.38 is equal to 3 multiplied by our wavelength. And when we go ahead and divide by 3, we find that our wavelength in this case is going to be 0.46 meters. From there, knowing that frequency, we can go ahead and find our velocity. So velocity is wavelength times frequency. So it's going to end up being this 0.46 multiplied by our frequency here, 196.23, and we end up with a velocity here of 90.3 meters per second. So moving on to part B here, we now want to consider the fundamental frequency of this string, which is the m equals 1 case. So same basic equation here, m lambda over 2, but we're now going to say m is just equal to 1. And so when we go ahead and solve for our wavelength, the fundamental frequency will be a wave with a wavelength of 1.38 meters. And if you want to visualize this for a second, that would be 1. Again, it's fixed at both ends, but it would just be oscillating like this, creating that standing wave there. So from there, we can go ahead and use that wavelength to solve for our frequency. So we can say velocity is wavelength times frequency. Even though we're discussing a different harmonic, the velocity of the wave on this string is going to remain the same. Our wavelength is this 1.38. And we can go ahead and solve for our frequency. So our frequency will end up being 65.4 hertz. So moving on here, we have another problem involving an organ pipe, and this organ is playing the note middle C, which has a frequency of 262 hertz. Keep in mind that the note you actually hear is going to be the fundamental frequency, so while there will be harmonics at play here, what you actually hear is that fundamental frequency. And so what we can start with is our equation for a pipe that is open at one end, m lambda over 4, where m is 1, 3, 5, etc. We are dealing with the fundamental frequency, so if we want to visualize this, the one end is fixed, the other end is open to oscillate, and so that sound wave within the pipe would look something like that, the fundamental frequency, that is. So if we first are able to determine our wavelength, which we don't know yet, we can easily find the length of this pipe. So in order to find the wavelength, we're going to say velocity is just wavelength times frequency. Because it's an instrument that relies on sound traveling through air, in this case a pipe, we're going to use the speed of sound in air, which is 343. So that's going to be equal to our wavelength times our frequency, which is 262. And so we find that our wavelength here is going to be 1.309 meters. Okay, so we can go ahead and sub that wavelength in there, and then we can find the length of the organ itself. The m here is 1, the wavelength is 1.309, and 4 is going to be on the bottom there. We go ahead and solve for that and find that the length of this organ pipe must be 0.327 meters. Moving on to the second problem here, problem B. We want to know if we instead filled the pipe with helium, what frequency would that play? And so one of the keys is the length is going to be the same here, even if we fill it with helium, and therefore our wavelength will actually be the same as well. The length of the pipe hasn't changed. We're still talking about that fundamental frequency, and so this will be a case where the wavelength of this new wave, even though the velocity has changed, the wavelength has remained the same. And so we can just jump right to the velocity equals wavelength times frequency equation. So this faster speed in helium is going to be equal to the wavelength, which is still 1.309. And again, I just got that from the original wavelength here, times my frequency. And so when I solve for that new frequency, I'm going to find that it's going to be 767 hertz. And so, much like when you fill your air with lungs, you have a much higher pitched voice. A very similar thing is going to happen in this case when we fill the organ with helium. The frequency, which was 262, becomes significantly higher, 267 hertz.